Hi, everybody. I think we're in the main session now. So welcome to this session on reproducibility in large-scale studies. It's great to have you all here today. I've just got a few announcements to make before we get going with the talks. So first of all, just to let you know that this session is being recorded and broadcast live. And it's obviously on Crowdcast here and also available on YouTube, where there will be transcriptions available if that's useful for you. Please be aware of the MRI Together Code of Conduct, which can be found on the website. And during the talks, you're free to ask questions in the Q&A box, which you can find on the right-hand side of your screen. It's different to the chat box, so just be aware of that. And please also upvote any questions that you see on there that you find interesting and relevant. And we'll come back to those after all the speakers have finished in a kind of discussion session at the end. And just to let you know, all ideas and questions are welcome. There's no such thing as a silly or stupid question. So just ask away in there, and then we should have a great discussion at the end. Okay, so I think that's everything announcement-wise. So I'd like to introduce now our first speaker, Dr. Penny Hubbard Cristinacce from the University of Manchester. She's the lead of the MR Core Lab at the National Cancer Imaging Translational Accelerator. And she's going to be talking today about improving the quality of quantitative MRI biomarkers in multi-center studies.
Thanks, Ellie. All right, can we see my slides? Yes, all good. Okay, so yes, as Ellie says, my name's Penny, and I'm going to talk to you today about improving the quality of quantitative MR biomarkers in multi-center studies. And sorry, let me get onto the right screen. There we go. So yes, I'm the MR Core Lab lead for the National Cancer Imaging Translational Accelerator, or NCTA for short, and we are a network of medical imaging scientists and experts, clinicians working across the UK in order to develop an infrastructure to aid clinical translation of quantitative MR and other imaging biomarkers. So I work in Manchester, which is here, but I work with colleagues around the country in this multi-institutional consortium of imaging centres. And we work in 3 cross-institutional units. So we have an imaging-focused clinical trials unit that works on the regulatory aspects of trials. We have a repository unit who is looking at the storage and sharing of data using the XNAP platform. And I work in the QA/QC unit, which is there to improve the quality management of our imaging biomarkers and provide integrated pipelines and quality assured imaging biomarkers. And as part of that, we're developing an MR Core Lab. Additionally, the grant, which is funded by Cancer Research UK at present, allows us to engage with other stakeholders in the clinical translation pathway, so industry, funders, regulatory agencies, etc. And we're also looking to establish consensus guidelines for the translational pathway, not only of MR, but also of nuclear medicine biomarkers. So that's just to set the scene as to where I'm kind of coming from here, but I want to broaden the talk out a little bit more about clinical translation in general later on. So just an overview of what I'm going to talk about. I'm really just going to whip through a why, what, how, who, when, in terms of improving the quality of quantitative MR biomarkers. So first, why do we need to improve quantitative MR? So we know that there is vast potential for QMR, not only to enhance personalised medicine, but in understanding diagnosis of disease, prognosis, etc. And in the past 20 so years, we've seen an increase in not only the number, but the scope and popularity of these methods. Some of this is down to improved quality and speed of hardware and software, but we can really extract a really broad range of either MR-based characteristics or physiological characteristics from our data, and that list is not comprehensive, I'm sure. However, we've found that not many of these methods have really translated into widespread clinical adoption. So I kind of think of the academic environment as being this kind of spring from which these new and improved QMR biomarkers emerge. And they have emerged. There have been some translation. So biomarkers such as left ventricular ejection fraction, TNM, for instance, have moved into clinical practice by being long established, by having some obvious clinical utility. We've also seen translation through commercial routes, so examples such as FeroScan, a liver iron concentration biomarker, has been supported by companies. It's got associated IP and has moved in that way. But what NCETA are really trying to do is try and break down some of these barriers that are stopping the academic biomarkers moving into the clinical environment, and work out how we can better understand that translational pathway. And part of that is doing multi-center studies. So kind of what do we need to improve? I think it was Gareth Barker yesterday was talking to us about variability in the quantities that we calculate from QMR. And some of this is down to the different vendors. But we also know that the same vendor and different sites can still see variability in these quantities, or the same scanner on a different day. So to translate biomarkers, we really need to understand reproducibility, particularly a lot more, in order to determine how reliable they are to be used as imaging endpoints at different institutions. And I want to impress upon you today that that's not just in terms of our data acquisition. We also need to think in terms of reproducibility of reconstruction, but also data analysis methods as well. And if we're really going to talk about quantitative MR being quantitative, we should really be able to kind of relate these quantities back to SI units. So we need to be working with our measurement standards agencies in order to improve the traceability of imaging biomarkers, or quantitative imaging biomarkers, back to SI units. So recently, myself and some colleagues published a paper in Physica Medica looking at this subject, so clinical translation of QMR, and providing an overview of the current landscape, and also a gap analysis to where we think we could be. And a lot of the work that's actually been presented here at MRI Together is really key to that change and closing that gap. So this is a UK focused study in many ways, in that we also did a survey of the UK MR community, and we asked questions such as this. So what quality assurance data is acquired and processed on your MRI clinical research scanners at your institution? And we found that 85% of the institutions perform some sort of vendor QA metrics, which I'd argue is probably not quite enough. I'd like that to see that closer to 100%. But as we move towards quantitative MR metrics, that number drops by 30%. When we move on to the actual data, what happens to the data after it's been acquired, and ask about the quality management procedures to oversee the data analysis stage, we find that although most have some SOPs governing data analysis, for instance, data quality checks of the scan data, only 36% of sites. And when it comes to checking the data analysis validation, only 9%. So we've seen a decrease on the quality management aspects when it comes to what we do with the data. So it's probably no surprise then that when asked, does your institution have any software quality management system or code review in place, only 21% of sites had anything. And so we've really seen this sort of decrease in quality management practices from acquisition through to our analysis stage. So how do we improve quality? I'm going to go through a few questions here, which we were asking ourselves when we were developing the MR Core Lab, and in particular in terms of multi-center studies. but I think they are relevant if you're just doing a single center study as well. They're quite simple, but can your scanner acquire the necessary data? So we need some form of evaluation as to whether or not a scanner should be included, particularly in a multi-center trial. Often sites are chosen based on the patient population and not considering the fact that the software release might not be what we need in order to perform that imaging method, or we may not have the right ancillary equipment available. And we want to know that as soon as possible. Is your scanner acquiring data that is comparable with other scanners? So we know that there's variation between scanners. There's different ways in which we can think about harmonizing and standardizing protocols, but we need to be thinking about that early in the process and deciding what is acceptable in terms of differences between scanner data. Can your scanner acquire good quality data that can answer the study questions? And we know that the scanner can acquire the data, but can it do it well enough? So each scanner should undergo a qualification in order to assess the quality of the data, and that can be done using phantoms or healthy volunteers or perhaps some early patient data. Can your scanner maintain this quality for the duration of the study? So we need to be monitoring the study. A study can go on for a number of years, and we need to ensure that the quality is maintained throughout. Was the data acquired as per the imaging protocol, and is the data quality sufficient? So some data QC on the acquired data is important. We need to know if there are any variations from what the protocol was and how that impacts data analysis before we move into that stage. And then finally, did the code undergo review? Was your analyzed data quality sufficient? So as we've seen earlier, a lot of code is used, in-house code is used that has not gone under any code review, is probably not well documented, etc. So we need to think about the analyzed data QC as well. So it was these questions that fed into development of what we do at the MR Core Lab. So if a new scanner comes along to a trial, we have a scanner evaluation period, and this whole blue oval here is really our full scanner assessment. So we've got evaluation, we've got an imaging protocol review meeting where we talk with the study team about protocol harmonization and what we need to do to improve that. We have a technical imaging visit prior to qualification where we acquire some data from a phantom or a healthy volunteer in order to be able to compare that to the live study data as it comes in, and also to assess the quality of the data. And at this point, we can lock down the imaging protocol and qualify the scanner for use in that study or trial. So we have a lockdown data acquisition. And then once we have a qualified scanner, we can move into the image data review and analysis part of our assessment, where we upload the data onto the XNAT repository and perform ongoing data QC, both on the data acquisition, and then we can also integrate our data analysis into that XNAT pipeline and also do some QC on the analyzed results. And as I mentioned before, monitoring of the scanners is really important. So I've got the lockdown data acquisition there, so analysis. So we want to monitor our scanners, and we do that using our QoS. We use Qples, where we can not only document who has read the relevant documentation, but we can also track things such as if there's any upgrades to the scanner, if a coil needs to be replaced halfway through a study. And so then we can trace that back to any discrepancies in the data QC, and we can remove data from a study if necessary at that stage, as opposed to cherry picking once we've done the analysis. So just moving on to the acquired data QC in a bit more detail and how we're using XNAT to do this. We have a lockdown data acquisition here. As I say, the data is uploaded by the sites onto the repository. And then we can use a container service within XNAT in order to perform some protocol checks. So we containerize the code, and we can perform checks of all the DICOM headers compared to that data that we acquired on the phantom at qualification. We can also use the integrated OHIF image viewer in order to do some checks of motion and alignment, artifacts, etc. But we are looking to try and automate this a little bit more. So we're very interested to talk to anybody that has automated QC processes available. Next, using XNAT in a similar sort of way for the data QC, the data analysis stage, we have lockdown data analysis pipelines, and we're trying to create this library of data analysis tools, which, as I say, uses container service within XNAT, where you can run a container within XNAT and interact with the Docker image, which contains the lockdown data analysis protocols. And so far, we've been doing this using MADAM, which is a quantitative MR analysis package that was been developed in Manchester, which looks at DCE, dynamic contrast enhanced imaging, and diffusion. But we are looking to work with other teams who have good quality code that is well documented and version controlled and has undergone good quality management practices, and try and integrate these tools into our pipeline to make them available to a broader range of studies. So like I say, we get this whole integrated pipeline, the whole workflow from upload of the data through data QC, through analysis, all in the same platform. It's really easily accessible. So who needs to be involved? From an MR Core Lab point of view, we're really looking at supporting these three groups. So clinical study teams, perhaps they're using an established biomarker, but in a new patient cohort, and want to roll that out into multiple centres, don't necessarily have the MR expertise within the study team to support that. They could use the MR Core Lab. Subject matter experts, perhaps you've developed a novel biomarker or an improved biomarker, and you've tested it out and it's working great at a single centre, but you'd like to test reproducibility and see how that works across multiple sites. Again, we can help there. And because we've got a fully auditable pipeline, we can, from acquisition through to analysis, we can also work with pharma companies who are using QMR biomarkers as in order to demonstrate clinical efficacy of their drugs. But in the last sort of 5 minutes, I want to just open this out a little bit in terms of who needs to be involved and who needs to be involved in improving clinical translation of QMR. And we have loads of great studies out there, and apologies if I've not highlighted yours here, but it's just a flavour of the work that's done. But there's quite QA and multi centres for diffusion, for spectroscopy, using phantoms and travelling volunteer studies for DTI there. There's a very recent paper by a neuroimaging network using the ACR phantom in order to test reproducibility of different scanners in that network, and looking at scanner upgrade effects, etc. And kind of traditionally, this work's often been seen as a little bit boring, a little bit kind of not very sexy, I think I was told. But it's so important to as actually enacted change and getting these biomarkers into clinical translation. Similarly, we need to think about what tools are out there, what are available, and how they can work together, and how we can bring the best things together in order to enact change. I think we've got harmonized imaging protocols. We've got system phantoms, open data, open analysis methods such as QMR Lab. Tools such as MRI QC, which are for image quality metrics. I don't want to be reinventing any wheels with the MR Core Lab. What we really want to do is bring together the best methods and ideas that are out there, and make them accessible and standardized and as good quality as possible. And I think one way we can start to do that is through the networks that have already been created, and such as Kiba and Quinn and eyeball, and some great work that was done by the UK Renal Imaging Network, producing consensus documents for both acquisition and analysis, in that case, of renal imaging. So there's really great work out there. But what I would like to see more of, I think, is really networks of networks. So networks of people understanding and working together in order to better understand what we can achieve, but what that translational pathway is for QMR. And I really like to kind of enthuse young researchers in finding clinical translation as something that's really important to them, and understanding where they are in that translational pathway. Not only, you don't have to necessarily be the person that's taking your biomarker the whole way, but I think you should really understand who you should be passing the baton on to. And so this is again not comprehensive by any means. I just wanted to make a pretty picture, but there's a whole networks, and there's how can we work together better to improve clinical translation. Now, last question is, when do we need to do this? And it's thankfully a very quick answer. It was yesterday, wasn't it? So let's keep working together. Let's find ways in which we can understand the stakeholders involved more and understand their perspectives. And yeah, I think that's where I want to finish. So just thank my colleagues at NCTA across the country, and anybody else I work with, co-authors of our recent paper, but also the co-organisers of a workshop that we held as well, Steps on the Path to Clinical Translation, at the recent British and Irish chapter of ISMREM meeting. The organisers of MRI Together do an absolute great job. Loving this conference again this year. If you have any interest in what we're supporting at NCTA, please go to the website or follow us on Twitter, and there's my email address if you want to get in touch. But I'm obviously happy to hang around and answer some questions after the speakers have finished. So yeah, thank you very much, and I'll hopefully chat to you later. Thanks. Bye.
Great, thank you so much, Penny, for that talk. It's really interesting and inspiring, actually, to hear about the work that you're doing. Yeah, please, anyone now, while the questions are fresh in your mind, put them in their Q&A box, and hopefully we can have a good discussion at the end. But now we're going to move on to our next speaker, Professor Jongho Lee from the Department of Electrical and Computer Engineering at Seoul National University. And he's going to be talking to us today about generalization, performance, and reproducibility in deep learning for quantitative susceptibility mapping. Over to you.
Okay, thank you very much for inviting me for this opportunity. And my talk will be a little bit different in terms of its focus and also the target. So it's more like you are developing a method, a quantitative method, that maybe in the future will be translated into the large-scale studies. But still, you are hoping to make sure, and we have this deep learning part inside of it. It's the technology is based on the deep learning. And then you need to check a lot of different things to make sure that it can be used for the large-scale studies. So it's more like a single method, single quantitative deep learning method that you have to see a multiple spectrum of it so that you can make sure that it can be translated for the future large-scale studies. So it's about QSM, and it's about deep learning for QSM. I start, deep learning, as we all know, it's a really popular topic. I believe it started with the data analysis, where we can do the segmentation, identification, detection type of research. After that, we begin to move on to this image reconstruction, from case-based to image domain, or some kind of QSM type of reconstruction that I will talk about soon. I believe now people are looking into this data acquisition as well. So my group has developed a method of designing an RF based on the deep learning. There are researchers doing the sequence design based on deep learning. So the topic never ends in deep learning, and it's still very exciting. So let's begin with the QSM. As that's the main topic of today's presentation. If you're new to the QSM, it's a way of quantifying magnetic susceptibility by using MRI. It's a very fascinating, method in a sense that, like physical quantity, the susceptibility can be measured directly from MRI. And in the brain, we have roughly two sources that are responsible for the susceptibility. One is iron complex or protein, and the other one is myelin. And in some disease, we have some concentration of iron, like hemorrhage. Or if you have like MS, you have this demyelination lesions. So they are useful in clinically as well. The physics of QSM is also fascinating in the sense that it follows the signals and system class or Fourier transform in that perspective. So if you have this susceptibility distribution in your head, what we can measure as the result of susceptibility is this susceptibility convoluted with the dipole pattern shown here. And that's what we measure in our phase image or frequency shift image from our scanner. So to get the original source image, what we need to do is doing this deconvolution of the dipole pattern from that field map that we acquired from the MRI. And that's our magnetic susceptibility map. And naturally enough, the Fourier transform helps us to understand the whole process. And it becomes the multiplication and the pattern of the dipole changes to this cone surface at 3D in Fourier domain. And that's our relationship. Now we all need to do is do the Fourier transform of the phase or field map, and then divide it by this 3D pattern shown here. It's in 2D right now, but in 3D, that's the shape of it. The bad news here is this cone surface has 0 values, and you cannot really divide it by 0. So there comes the problem of the QSM. How to fix this problem by multiple different approaches. One of the simple approach to overcome this underdetermined problem and make it into the overdetermined problem is by changing the data acquisition. Instead of acquiring a single orientation head data, you rotate the head, acquire the data one more time, rotate head another direction, acquire one more data set. And if you do it like 5 times or 6 times, then you can get rid of these 0 values, making the problem as overdetermining the problem and generate a high quality Cosmos or high quality QSM result. And this method is what we call as Cosmos QSM reconstruction. It's gold standard, but it's not practical as you cannot really ask your patient to do the multiple head orientation scan. Instead, people have been working very hard to make a single orientation data to be translated as a nice QSM research. They are practical, of course, single orientation, 5 minutes, doable, but it always contains errors as expected. And these are the results that you can get from different reconstructions. That's the Cosmos, our gold standard result. All the others are different reconstructions of QSM. They usually contains a lot of streaking artifacts that hampers our accurate estimation of the susceptibility values. So there comes the savior in certain sense, that we can utilize our, the power of the neural net so that we can improve the quality. And in every sense, this QSM has a unique opportunity to improve its image quality by using neural network, because we can acquire this Cosmos high quality result or gold standard result by spending a lot of efforts and time on the data collection. Then you can train the network with a single orientation input and the full Cosmos reconstructed QSM result as the label. And by having multiple pairs of them, you can train the network so that the network learns how to solve this problem of deconvolution by looking at the pair of the data. So it's a supervised learning, simpler supervised learning approach. And then for the inference, you no longer need multiple head orientation. You only need a single orientation data set that can be inferenced to generate this gold standard quality maps. And that's what we developed in the lab. That's QSM-NAP. Or you can use other approaches of simulated data sets so that you can have this deep QSM result as well. And this is one of the examples that I really like to show you, in a sense that you can compare the image quality directly. That's the gold standard That's the neural-led result. These two are conventional research reconstruction that give you some artifacts because it simply uses the single orientation. Again, these three utilize the single orientation, and you can clearly see the advantages of the image quality in the QSM-net. Well, since that research, there has been a lot of results and new proposals of QSM using neural networks. Some of them utilize a way of not using the brain mask for the QSM generation. Another approach is simply using this filtered base image to reconstruct the QSM result. GAN has been proposed to improve the image quality, and people went outside of the brain so that you can fix the issue of the fat by using the neural network. So this topic has been, widely successful in certain sense, but it turned out to be, it has a lot of different challenges, and that's what the focus of today's presentation is about. And I believe that's the issue of largely reproducibility, if you broaden your scope of reproducibility. And the first issue that I want to talk about is this generalization issue of the neural network. And what do I mean by generalization? So if you think about the network that are trained by a certain characteristic data set, for example, my QSM-net is only healthy volunteers, 1 millimeter isotropic voxel size, done at 3 Tesla. Now you are using it for large-scale studies, then you may expect different input. You may scan patient, of course, and you may have different resolution for your input data set. That's something that you can harmonize it, but in larger sense, you may not get always the same resolution. Sometimes you get different field strength. There has a lot of more problems, but you can, just natural way of using it is using the same network for every inputs that you can think of. Another one is pre-processing can be also different from the data to data sets. Now the question is, will the network give you the same high quality result for all these different type of inputs? And the other question is, what are these type of input, parameters that may affect the performance of the neural network? So what we have explored so far was two things. The first one is susceptibility range. As I mentioned, the QSM-net was trained by healthy volunteers only, so it has a certain range of susceptibility, relatively narrow. And the network has never seen a value like hemorrhage that has very high concentration of susceptibility. So that's something that network never has seen it, in its training data sets. And when we utilize it when we use the QSM-net to see how well it behaves for such lesions, what we observed was the fact that it underestimated susceptibility values in those hemorrhage lesions. So that's the problem. QSM is quantitative mapping, so you have to get the values right. But here we had an underestimation, which is a problem. And we proposed the way of doing the data augmentation by model so that we can overcome this problem. And the network is now called as QSM-net Plus. So that's one direction that you have to make sure that your network performs well so that you can use it for large-scale studies. Another one was this resolution. So as I mentioned, QSM-net was trained by 1 by 1 millimeter voxel size, but some places may acquire the data at different resolutions, like 0.5, 0.5, 1.5. That's one of the popular resolution acquiring the QSM data set as it is done in clinical environment. And as you can see here, these are all the results of the inference of QSM-net based on different resolutions. And if you compare this result, where the input resolution of the inference data is the same as the training data, there's no problem at all. But here, if the voxel is anisotropic and different from the trained network resolution, you can see a huge errors in the result. So that's a problem. You need to generalize for resolution, but it doesn't. And if you think about why this happens, it really depends on the deconvolution kernel that you developed, and that's a voxel size dependent. So you need to develop a way of overcoming this resolution issue. And there has been research that has been proposed to overcome the problem, and the more papers are coming up in this direction. And some of them utilize the new network architecture like octave convolution so that you can have better processing of low and high frequency information. Some others use the indexes so that you can use that information, resolution information, directly into the neural network. But again, that's something that is in progress to solve the problem. So we really need to focus on those problem sets as well. Well, there are general approaches of improving the performance of this generalization. And that's by using some of the neural network that utilize not only this end-to-end trained network, but also combining the model into the reconstruction process along with the neural network. There are 3 papers that I show you here, and some of them have a better performance that to this generalization. So what I want to say about this generalization topic is when you design a network, you need to evaluate your network, whether it needs to be generalized for certain parameters or certain conditions, so that you can make sure that it can be applied for other populations that you're studying in the future. The next issue that I want to talk about is this rather, another interesting topic. It's a performance comparison and reproducibility. So that fits better to this presentation, the topic of this presentation. So when it comes to the performance comparison, that's something that you are supposed to do when you write a paper. So here's one neural network, you design another neural network, then you need to have a fair comparison of the performance of the 2 networks. But unfortunately, in QSM, along with a lot of different fields in medical imaging, especially in MRI, there's no public data. There's no large size public data available. And that's a problem. And everyone is using their own private data sets so that they can train the network and evaluate the network. And the problem of this private data set is they have different characteristics. They can have different resolutions as shown here. They can use different pre-processing. And also, like their label can be different from one to another. They cause a lot of troubles when you do the performance comparison. And if you think about what you can do about comparing 2 different neural network performance, there are 2 ways of doing it. The first way of doing it is you grab a pre-trained network that are trained by some previous data set, and now you have different data set like data set B, and you are comparing that pre-trained network with your network that are trained by your own data, again data set B. And for the evaluation, you want to use the same data set B, as that's the only data available at this moment. And then you report the SSIM score type of quantitative metrics. This cannot be okay comparison, because this data set, if that's different from that data set, then you're literally comparing apple and orange as shown here. So if the network was trained by like 1 by 1 by 3 millimeter resolution and evaluated by 1 by 1 by 3 millimeter resolution, the previous network that are trained by 1 millimeter isotropic voxel size will have obvious underperformance based on the resolution issue. Well, that resolution is a pretty big difference. So you may match the resolution perfectly, but still very minor pre-processing step still can give you a substantially large side effect, as shown here as the pre-processing steps of QSM. So literally this comparison is very difficult to argue if you are writing a paper. Another way of doing the comparison may be you grab the network architecture itself, and then you retrain the previously published network by your own data set. So now, at least in this comparison, you utilize exactly the same data set for the network training as well as evaluation. So it may seem that you are doing a fair comparison of the 2 networks, but the reality is not. That's because neural network is not about the neural network architecture itself, but it is also about the data sets. So they are combined together as a single neural network. So when I say QSMNet, that does not mean that the 3D unit structure of the QSMNet. It's about the QSMNet structure along with the data set. So what I can argue as an additional point outside of that argument is that if you retrain the data set with your network, with your own data set, you may need to do the hyperparameter optimization so that you can have a slightly fairer comparison between based on your data set itself. And then you can easily find a better performance by doing the hyperparameter optimization. But still, this comparison is not fair. Again, if you change something on your neural network, that's not a fair comparison. Well, one thing that we found out from this research is the fact that neural network has a very poor reproducibility. So if you have one seed and if you change the seed for the training, then you get a different performance. And this problem of getting the reproducible result is pretty big issue. And also, unless you find all the details of options to make the network reproducible, it's pretty difficult to regenerate the network from one lab. If you simply copy the architecture of the neural network, even if you get the same data set from them, you need to have all the minor instructions so that you can make sure that you can get a correct reproducibility of it. Having said that, the simplest way is sharing the weights along with the neural architecture itself. With that, you don't have to suffer from retraining the network, avoiding the issue of reproducibility. So as I'm getting out of time, let me go to the last topic. It's about the topic of performance itself. Many of the neural network are trained to perform a certain, metrics. Like for example, QSMNet is designed to optimize these a few parameter loss functions, and then the reports on the performance are measured by these kind of metrics that we generally use in neural network. And then if you see the result, QSMNet seems to perform much better than all the other results. But this result does not guarantee you that it can do a better job in other metrics, like more important metrics, like iron quantification. So this is one of the results that I really liked that just came out live at the Neuroimaging clinical, and this is not from my lab, and I'm very excited about this result. What this one shows is this: out of these 4 different methods, QSMNet does a pretty good job in how it creates the image based on the eyes, and correlation with age, consistency with Cosmos result. But when it comes to the iron quantification, it does a very poor job as compared to the conventional reconstruction. The same is true for the segregation between Huntington's disease and healthy controls. QSMNet does a very poor job of doing it, and whereas the conventional method does a much better job. And now it's a question: what do we mean by better performance of the neural network? As here, the functional measure is quantifying iron or differentiating early, manifest Huntington's disease versus healthy controls. Neural network, even if it gives you a pretty looking images, it seems to fail here. Now the question is, why do we get such result? And what we can ask is, can it be just the generalization issue? Can it be, or can we design a new neural network that performs better on certain tasks? All of them are open questions, and all of them needs to be addressed before we go to the large scale studies. So it's pretty exciting time that you have to do a lot of deep research to get the methods translated into the larger volume. So this is my summary slide. So when we begin to work on this neural network, that's about 4 years ago, after getting the result, we thought it was we knew it was very exciting, but we thought it was the end of the result. But it turned out to be just the beginning of the result, and we can go to multiple directions to find a way to translate this neural network into the clinically useful method, and that may require a lot of thinking. And here are some of my thoughts that I listed here. And the one that I talked about is one example of the QSM, which is quantitative measures. And I believe many of our neural network that has been applied in different quantification may have similar issues. So I believe this can convey some of the important points that we may face in our research in the future. With that, I want to thank you for your attention, and this is my lab at Seoul National University. Thank you very much.
Thank you, Jongho, for a great talk. That was really interesting. And I think a lot of those issues definitely have, applicable to lots of other fields outside of the quantitative susceptibility mapping. So that was really good. Great. So as before, everybody, don't be shy about posting your questions for Jongho in the Q&A box on the right-hand side. And we'll now move on to the next speaker, the final speaker for this session, Dr. Paul Taylor. Paul is the Acting Director of the Scientific and Statistical Computing Core at the NIH National Institute of Mental Health. And today he's going to be talking towards transparent and reproducible neuroimaging research. So over to you, Paul.
All right, thank you very much. And is that visible?
Yeah, looks
Okay,
good.
great. All right, thanks very much, and thanks for inviting me. So I'm going to talk about what's mostly a visualization technique for representing results that we think is pretty important for improving transparent and reproducible research. And then also it has some consequences for how the analyses themselves are done. So as an overview, I'll just talk about the example data set that I'll use throughout this presentation. And then with a few different examples, we're going to talk about results reporting and looking at how it's done currently and maybe a better way of doing it, how this affects the information content in your data presentation, and how this actually helps improve cross-study comparisons, meta-analyses, reproducibility. So the data from this study comes from the NARPS project, which is publicly available. There are two groups of subjects with about 54 subjects in each. It's a task-based fMRI data with a mixed gambling paradigm. So fairly high-resolution data set. And what we did for the group level analysis here would be as if you're just doing a simple straightforward study with nonlinear alignment to template, blurring, and things like that. And in the interest of time, I'll skip the details on the processing, but all the scripts are publicly available and the methods described a bit more. But basically, the point of this data set being public was lots of groups processed it. And so they also have a cross-study comparison where 70 different teams described how they processed the same data set. Everyone was given certain research hypothesis questions to answer, and teams were supposed to analyze it in a voxel-wise way, however they wanted, answer some yes-no questions about hypotheses, and then to get a sense of kind of reproducibility from the point of view of variability of processing or how things go in the field. So I'll talk about our kind of processing results for just a simple group level description, and then also look at this kind of cross-study meta-analysis. So as a first example, I want to consider group level results as they're standardly presented. So you do your analysis, and then you do kind of standard voxel-wise threshold, say P of 0.001, and cluster-wise adjustment for multiple comparisons. And this is typically what a results in a figure would look like. Now, we're used to seeing this, and the idea is that my results are here, 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 where there's the red and blue blobs. However, if you notice, we don't actually see any information outside of that. So I have no idea if there's something just below threshold or if there's an artifact or anything like that. So this is a different way to view these results with what's called transparent thresholding. In this case, the supra-threshold locations are opaque and outlined. So they're still here as you would see them and highlighted now. But everything else, you can see results. And the idea of how this is presented is that things that are below the threshold are increasingly transparent. So something just below the threshold would show up as relatively bold and you can see it easily. And things that are well below threshold, it's just extremely transparent, almost invisible. So I actually have now information content everywhere. So I can focus on the same regions as before. You see toggling here. So that same aspect of these are the super threshold ones is there, but I have information everywhere in the brain. And it's a pretty simple idea going back to a paper in 2012 by Vince Calhoun's group. It was never really picked up, but when you see the results like this and like this, I find it hard to believe that these are really kind of viewed as acceptable because we analyze data everywhere in the brain. Why not show results everywhere in the brain? And we even suggest not even threat masking within the brain, but show results everywhere. This actually helps avoid a lot of quality controls issues. And the fact that there are kind of scattered bits out here, that's okay because you want to know if there's structured noise in your results and things like that. So as you see the kind of information content that's here about your analysis, we view this one as really a lot more scientific, and actually it gives you a lot better sense of what's going on in the brain. This method promotes an interpretation that says that these parts of the brain are active and nothing else is, and that's just not biologically feasible. That's not how the bold mechanism certainly works. This is a lot more realistic and matches a lot better with the actual methodology that we're using. And it is true that we live in a day and age where people can upload their results and are encouraged to, and that's great to put things on NeuroVault. This is very separate because how you visualize your results and talk about them in the paper, that first instance where the reader is looking at your work, really influences what you say and how it's approached. And it's great to be able to look up full results later on, but it actually takes a lot of work. And when you kind of craft what your results mean and how someone else should look at them and think about them, it's worth knowing, is there something here that looks like it might be a real region involved, maybe with a few more subjects, maybe with a slightly different paradigm and things like that. You get none of that information here. So there's a host of reasons why having this greater information content is really useful. Okay. Another way that we can approach this issue and why we might favor the kind of highlighting methodology with transparent thresholding is let's think about what neuroimaging analysis really does. One way you can think about it kind of zoomed out is you start with a bunch of raw data, and right, we don't publish this. I don't say here's 100 subjects, go look at them. Somebody processes them, analyzes them, and as you do that, you're kind of reducing the information content there in some sense. Some of this processing is to remove noise, artifacts, and things like that, but you're breaking down something like all the individual results. Typically what you do is you move toward group analysis, so you lose that kind of individual aspect in some sense, but you're getting effect estimates in a standard error map, let's say a t-test, ANOVA, multivariate modeling, whatever you're doing. And then you can choose how far along in your processing to keep going. And as you keep churning your data through different analyses, you're kind of losing information content. So for example, when you do fMRI, you get a beta weight map and a standard error map. You could use that, or you could just show the statistics only, or you could dichotomize your results and threshold. And then many times actually people kind of report the peak only of their data. As you go through there, your data is losing information. the reason people tend to do it is because it's getting more digestible and it's easier to understand. And this is something that we kind of deal with as a balance within science. We want to reduce the information to something understandable and hopefully focusing on real effects. And we're also trying to make it more digestible and, again, describable, because the paper can't be, here's 100 subjects, this is subject 1, this is subject 2, etc. So we kind of have to strive for a balance of these competing effects. We don't want to lose too much information, but we also need to make things digestible. On a side note, for a little bit more of a comment on this kind of choice that people tend to make to only show the statistic versus the effect estimate in the standard error maps, I'll just point to this paper in the interest of time. So let's think about this from the result of what I just showed. If I'm thinking about what should I show from my group level results, this is, let's say, the whole brain map everywhere in the field of view, unthresholded. And if I think about here, I've processed my data, so I've already kind of churned through some information and gained a lot of digestibility to have a group level map. Now I have to choose, what should I show this? Or maybe I should use this transparent thresholding. And I've reduced the information from here to here, but this is a little bit more digestible and understandable. I think we could all agree both those characteristics. Or I could reduce the information content further, because now all I know is these are sub-threshold regions, but I have no idea about them. I've lost information, but I have fewer things to talk about in my results. Or I could do, again, what unfortunately is a very common thing, to only report peak voxels and focus on those locations. If you see here, there actually is one red dot here. These other regions, because the peak didn't appear in this slice, I don't even see it. And you can see there's a huge amount of information lost from here to here, because the blobs that I have actually span probably several sulci and gyri and have complicated patterns, reducing a complicated folding pattern region to just a single peak voxel that's probably dependent on an unstable statistic location really loses a lot more information. But it's extremely digestible. I just now have, a dozen locations of the brain to talk about, and that's very easy to focus on. So as we think about this, my different choices from an information loss and digestibility point of view look like this. And I think I'd make the case that this first one is probably not something we'd want to publish in a paper, because it's not really digestive enough. It just shows a bit too much, and it's a little hard to focus and know what the focus really is. It's hard to do science on that in an image. Conversely, I think these images actually lose quite a lot of information, because with these two, you lose 95% of the results in your brain. And just saying, oh, nothing happened here, trust me, I think is not really valid or good enough, because if we do different studies, we have different paradigms or the different numbers of subjects, of course we're going to have slightly different results. And these methodologies like this make it look like my paper has decided that nothing is active over here. And that's simply not the case. My paper isn't powerful enough to decide the ultimate answer of which brain regions are involved in this task. I'm providing evidence for it, so let me provide evidence everywhere in the brain. So from balancing kind of digestibility and information loss, I really think that this balances a lot of those things pretty well, and it removes a lot of problems that people see with reproducibility issues. Or if nothing else, it allows us to actually see what are my whole brain results, and that allows us to actually accurately assess reproducibility. This is something that we can compare across studies in a lot more reasonable way than these thresholded ones, where we're actually comparing data sets where most of the information is hidden. Okay, and on that topic, in the third example, what does this really matter for kind of group level comparisons or for reproducibility? So I've made kind of a hand-waving argument. So let's look at the NARPS results. These are the individual team results. So this is the same slice of the brain across all different teams that participated. And if you notice here, as you move along here, I hope it's reasonably sized on everyone's screen, there's a lot of similarity in some of these results as you move along. Okay, so these are thresholded in the traditional way, all or nothing. And fine, we might say these are similar. There's some differences, sure. These red regions kind of come and go. The blue ones maybe here. As you come down here and I start looking at these brains, I might start thinking, wow, I see the big blue region here and I don't see one here or here or here or here or here or here. fMRI, all these teams analyze the same data. There's really a problem here because the results are extremely different. I might say that there's a huge amount of variability across the results looking at these images. I think that's certainly a reasonable impression from this style of looking at it. So now let's swap over to looking at the transparent thresholding view. And now if you look here, you still see the same kind of blue and red patterns. If you come down here to before where we saw nothing, if you look closely, you see when you can see transparently below the threshold, there actually is blue result here and here, just like here. And even down here and here and here. And the kind of the red patterns as well are similar, just a lot weaker. So if you look at this and you look at this, you get very different impressions. This, you might say, things don't agree. Here, when you look at this, you see that actually the directionality of the effect matches in virtually all the brains, in the predominant majority of them. The difference is that they disagree or they have variability in the strength of their agreement and their pattern. Those are two very different things. To say that something disagrees or it agrees with a different degree of strength is a fundamentally important difference. And when people look at the NARPS result, if you do a meta-analysis based on thresholded results, you might say there's a huge amount of variability. If you do meta-analysis or a comparison based on unthresholded results, what you're going to come across is you will say that things agree with a different degree of variability. And again, those are two very different messages. So how you, one way to look at this is a lot of people, I think, looked at the NARPS results and they said, you know what, there's a huge amount of variability due to processing. fMRI has a huge reproducibility problem. But if you look at a meta-analysis that doesn't insert strict, opaque, all or nothing thresholding before you compare your studies, you actually see what is really there in your data. It happens to be, in this case, a large degree of agreement in the effect size and sign, or the effect sign. The only thing that matters is the different studies, because of the variability in their analysis, which was, it was allowed to be quite flexible, the way people did things, different blurring radius, different modeling considerations, whether to use the size of the gambling estimates or not to modulate, a huge amount of variability, that's fine. But actually these studies mostly agree. And if you look at this kind of quantitatively with similarity matrices, your impression from looking at dice maps, where the threshold matters, is you see there's a bit of agreement, and then this is the team and team, the kind of similarity matrix, and the agreement is really dipping down for either the positive or the negative regions. If you look at the Pearson correlation of these, which is akin to using transparent thresholding, what you see is there's a huge block of huge agreement. That's the vast majority of results. There are a few data sets that really don't agree, so they have almost no or very low correlation. And then there's actually another cluster of them that have their own block of agreement that's anti-correlated with the other ones. And if you see that, that's actually the fact that this is blue and red, and down here there are some that are red and blue. So these people's sign estimate is opposite of these, which again it's an interesting way to kind of be different from the majority of results. So either they're interpreting things differently, or there's a sign mistake. And there actually were, if you read the NARPS papers, actually there were discussion of people interpreting, and anyways, how people interpreted the sign of these mixed gambling things. But this is a very different set of results. To say that we have a huge amount of agreement, and then maybe some people with an opposite sign, which again is something to deal with, but that's very different than saying, you know what, things don't agree very well. Over here, you might say high variability, really a problem in the field. when you look at the results without that artificial step of thresholding, which places really, it really bifurcates data that's different in very small ways, very sensitively and very artificially, that here there's actually general agreement, but with a varied strength of result. And for some reason, this figure is actually in the NARPS paper. I only realized this when we were redoing kind of this study. The take home, this also applies if you just focus on the regions for the hypotheses that the NARPS paper focused on. So if you, for this given hypothesis, they didn't focus on the whole brain, they focus on certain regions, the same story applies. And actually the similarity is much clearer if you focus on the regions they focused on. But basically, to me, the take-home message of the NARP study should be not fMRI has a reproducibility problem because of variability of methods. It's that how you do your meta-analysis really, really matters. And inserting thresholding before meta-analysis really puts a huge bias into your comparison. You remove valuable information from your study, and now you make the results highly sensitive to your threshold. So what we started off looking at with transparent thresholding of don't threshold away meaningful results, by the time you come to meta-analysis, this is extremely important quantitatively. So quantitatively and even for understanding the results, if you insert the threshold, you've biased yourself that tiny differences now look magnified, whereas here you can really understand what's happening in your data because you're able to see everywhere. Okay, so in conclusion, what we call the highlighting approach to results reporting, rather than the hiding approach of hiding away things that are below this arbitrary, but really kind of magical seeming threshold, it improves your own view of your study, within your study, the information content there, and it also improves comparisons across studies and how you view your results in the field. And I'd really like to make the case that an individual study cannot provide an answer on anything. If I came here and said, my study shows that this part of the brain is involved in this, that makes it sound like I've solved the brain or this result. That's not the case. I'm providing evidence for a conversation about evidence for this effect or that effect. And I should prepare my data and my results to be compared broadly, shared broadly, and examined with a large number of data sets. And so using this highlighting methodology starts that conversation happening immediately. You can still focus on key findings. So again, the digestibility aspect is still there, but you get to show a lot more. And in the paper, we talk about how this applies in lots of different types of studies as well, region-based, things like that. Reducing information content with all or nothing thresholding. Hopefully I've convinced you that you're introducing a phenomenal amount of bias and information loss into your data. There's also mathematical characteristics. You're kind of asking for badness mathematically and things like that as well. So hopefully I've scared you away from that. And again, it matters for cross-study comparisons, and this is really about reproducibility. And I'm not saying that just because you show more data, the results will always look more reproducible. I'm sure they won't, but this is the only way you can hope to address reproducibility. And I think if you introduce thresholding, you've biased yourself already, and so you're not really getting an accurate answer of reproducibility. So thanks very much to a lot of the collaborators and to the MRI Together organizers on this. And I'll also just note that if I haven't scared you away from interest in these or other topics in that NIMH has a lot of support training at all kind of levels of programs. And if anyone is interested in any of these, I've included links in the presentation, and that'll also be made public as well. Thank you.
Great. Thanks a lot, Paul. That was a super, oh, I've turned my camera off. Super interesting talk. I think you've definitely put us all off that all or nothing thresholding approach. So yeah, I'd just like to thank all the speakers once again. I don't know if we can do like clapping on here, but I'll be giving you like a virtual round of applause. And now we can move on to the discussion part of the session. So we've got some questions in the Q&A box, but feel free to add more and have a look at those also and like upvote the ones you find interesting. So first of all, I'll start off with a question for Penny. This is from Stephen. Can you comment on the cost of doing QC for MRI properly? Scanner time itself typically costs around 500 to 600 euros per hour. How much extra do we need to add for QC if we are writing a funding application?
Okay, thank you. Yes, important question. So it depends, I think, is probably the broad answer. I'd encourage people to get in touch with myself or NCTA prior to putting funding applications in, because it depends on the level of support that you want. If we're thinking about getting support through NCTA, depends if you need to use a clinical trials unit, the repository, or just the MR Core Lab. Obviously, part of the cost in terms of improving data QC is acquiring some phantom data. Typically, we're only really looking to acquire phantom data at sort of yearly intervals throughout the study. So that's not a major cost of what we'd be asking. But we'd also argue that, putting that money in and getting that data saves money in the long run, and that if we're overseeing the quality from the beginning of the study and throughout, we can be aware and stop any issues that are occurring in terms of data acquisition problems or data quality problems at an earlier time point, so you're not losing data from your study patients or subjects. So yeah, it kind of depends on a number of things, number of patients or subjects involved in the study, number of scanner sites. Obviously, each scanner needs to be qualified, so that increases the cost, and then the level of service, whether or not you want us to perform the qualification or a qualification plus data QC or plus the data analysis as well. Yeah, I'm hoping we're trying to create an infrastructure that means that people have access to best practice, the best methods that are available, but also that kind of network of knowledge that we've got. So yeah, it depends.
Yeah, building on that, actually, I was just wondering about this kind of network of networks that you spoke about, and this idea, of like joining all these existing kind of silos of people working on in their little groups together into like a wider network. And I was just wondering if you have any ideas how that might work in practice, or what kind of routes you might envision that like would facilitate that happening.
Yeah, sure. Because I think a lot of it is actually just knowledge sharing, because I think we've already got lots of great tools out there, and I think a lot of the time we have created within our sort of silos really important steps forward in terms of open research, reproducibility, tools that are available. But sometimes somebody who's developed that for diffusion imaging might not know about that, and they may go about creating a similar sort of structure. So I think when I think about networks, I think it's about that knowledge exchange, but it's also about kind of reaching out to those other stakeholders that we might not be so familiar with within the academic environment. So, what do regulators actually want if you're biomarkers to translate into clinical application? What do the clinicians need? What do we actually have to do? What is that pathway? And I've been looking at this for years and I'm still not entirely sure. So, I think it's just really sharing knowledge. In terms of methods to do that, I mean, we've started in the UK to create a network within the British and Irish chapter of ISRM, where we've had the workshop, and we've started having those discussions and had perspectives of radiologists, radiographers, imaging CROs, metrologists, open science networks, for instance, talking at a shared event. Our next steps are really to try and kind of take that international, because it doesn't stop within a region. It doesn't stop within an MR technique. It doesn't. We need to broaden out before we can really focus in on dealing with the details. So we're looking to kind of take that further at next year's ISRM in Toronto.
Oh, that sounds fantastic. Great. Thank you very much. Okay, so then the next question in the Q&A is for Jongho, and the question is from Mo, and he would like to ask, what is the best practice for the researchers themselves to make sure that the results they're reporting are not due to a lucky seed? So this is relating to different seeds in the deep learning networks giving different results.
Right. The best way is, having enough training data sets that overcome the limitation of the randomity in the seed. That's usually not easy to collect. So that's the challenge that we are facing. And when we tried the, fast, MRI data sets from NYU, that data set was large enough that we have very little effect, statistically insignificant effect when you train the variational network with variable seeds. So maybe on that range, it also depends a lot of different parameters, and also depends on your neural network capability and weights, number of weights. But roughly that range of data sets for that task, it was okay to get, you don't get that lucky seed in the result.
Yeah. Okay.
Now that I'm here, thank you for the great talk. Can I just follow up on that? So wouldn't an approach where you train the network multiple times and test it multiple times with different seeds be reasonable? Is it a reasonable thing to do?
Well, that's another idea that that's one way of objectively report your network. But when you share the network, you ended up with sharing one of those weights. So, or if you share all of them weights, that means you have to infer multiple times to get the average effect of the results. So that may not be a very practical way of getting the network decided by that.
Yeah. Thank you.
Thank you.
Great. Okay. So next we've got a question for Paul, and the question is from Mo again, actually, and it is: how do you weigh the importance of thresholding versus no thresholding approach against replacing p-values with more informative metrics?
Sure, it's hard. I mean, I guess my first answer would be it's better to do both. I guess I would. It's a little bit funny in the field that. So I guess people often comment on the fact that fMRI doesn't have units, which is fine, but it is kind of scalable to something like local bold % signal change, and that seems like an informative thing, and it tells you a lot about your modeling. And it's a little bit funny. There are very few areas of science where you say, "Oh, I got a significant result," and someone says, "What is it?" And you say, "I can't tell you, but it's significant, and here's the significance." You don't see that in a lot of areas of science, and fMRI has accepted this, and it's a little bit funny, or maybe sad. I'm not sure which. So I don't know. If someone said, I have a great market product like this, people significantly like it more than the other one. It matters whether it's 51% versus 49% in a study group, or 89 versus 11%, something like that. Even if the plus minus values are significant. So, okay, I think people should do more to really put out their effect estimates and things like that. I guess if I had to pick one at the moment, I would say everyone is showing. So people may or may not agree with that, or they may decide they want a different metric or something like this. But everyone is showing statistics maps now. This is really a fairly easy change. There's no reason really. The technology exists to show these things, to kind of add, to basically use the opacity to tell you information everywhere. So I guess I would lean towards saying, like, this one is extremely doable, implementable, and it makes such a phenomenal difference toward reproducibility right now. I think it's probably a slightly more fundamental one, to not hide away. If you think about, you have 60,000 or so voxels in a brain, or 100,000 or something like that by the end of your analysis, you're hiding away, you show maybe a few hundred. So think about the fraction of information you're hiding away in your data. There's so many different ways you can look at it. And you say, when people are worried that reproducibility, my results don't look like yours, we're not even really looking at the full results. We're looking at just, tiny tips of icebergs and things like that. So anyways, I guess I would lean toward the transparent thresholding first, but I do think the other one's also important.
Yeah, I guess it's more of a kind of low-hanging fruit in a way, the way you described it, that, where you've got that information anyway, so
yeah,
you may
exactly.
share it. Yeah, fantastic. Okay, Stephen, I think maybe you had a follow-up for Penny on your question from earlier. Yeah, feel free to go ahead and ask that.
Yeah, hi. I got invited up on the stage, so I clicked OK. No, I noticed, Penny, you didn't actually answer the question. I kind of wanted to know a number. And I know you probably can't answer it when it comes to your particular service, but in general, right? So I'm writing a grant application. I'm having an MRI protocol of an hour, and I want to include like proper QC of my biomarkers. And I know it depends on the scale of the study, etc. But is it 50 euros or it's 5,000 euros or what is it? Because I think it's an important consideration, right? I think we all agree that it's important, and we all want to have as much quality control as possible. But ultimately, especially for publicly funded studies, budgets are limited, and you have to make choices. So. Yeah. And sometimes the choice is more
and make me say a number, Stephen,
right now. And less quality control. I mean, so just a ballpark figure for a typical study of, let's say, 100 patients in a cancer biomarker.
So if you're looking at 100 patients, say over, I don't know, 4 or 5 scanners, I mean, we're talking thousands in order to do fully, full QC of the qualification of the scanners and data QC on all the data that's coming through. So possibly tens of thousands. But I think it, again, if it's something that you want to put into your study and you've got an MR physicist that's prepared to do that, then you can probably factor some of this into that study at a lower cost. It's really just making sure you've got enough time on the scanner to do the phantom work and to make sure that you're monitoring the study throughout. But it is so important for us to do. And I think, again, what I was trying to get this idea of making sure we share resources and we do things in the best and most effective way. That's why I really, I recommend trying to develop infrastructure that supports that, so we're not all trying to do it slightly badly. There's actually a few people doing it well. So I'm happy to talk in more detail offline about exactly what you'd need for your study. But yeah, we're probably talking tens of thousands for a study like that.
Okay, thank you.
Thanks a lot. Actually, there's another question for Penny here in the Q&A. I guess more about the practical side as well. How often do the NCTA members communicate and meet with each other?
That's a nice question. So we meet primarily on Teams or other sort of networks like this. I mean, the pandemic had a positive effect for us in that, as a consortium working across different universities, we probably would have worked in a way that we worked in our silos at our universities and then met up every few months and told each other what we were doing. But kind of from the outset, we started working in a really collaborative way. So I meet with other MR Core Lab members at least once a week, and we drop each other messages all the time. And if we need to talk about something more urgently, we'll meet more often. The broader network, so the governance group and the operations group for the network meet on a more like a monthly basis, but they're in a similar way. It would be quite nice to actually meet some of the people that I meet with and know very well, actually face to face soon. But yeah, that's how we do it.
Cool, thanks. So yeah, last chance for anyone to put any last minute questions in the Q&A if you've got any burning questions left to ask. Otherwise, I'd like to thank the speakers again. It's been a really interesting session. I think all the talks have kind of given us different insights, you know, on the overall theme. I'd like to thank the organisers of MRI Together for the great work putting this whole thing on, which I'm sure takes like a huge amount of time. And there's just a couple of other things that I need to let you know about. So you can look at the programme on the MRI Together website for details of future sessions. There will be sessions every 5 hours. So yeah, keep an eye out for the other exciting talks going on. Yeah, thank you to everyone who's attended as well. I think it's all gone really well. So yeah, thanks a lot. Bye.